as a neural network, I'll only think of weights. Right? But if I use this, if I view this as Bayes network, the same thing, sometimes I say hey, it's a neural network, sometimes I say a Bayes network. But if I see it as a Bayes network, I need to provide the conditional probability distribution. The distribution of this given these. Now the conditional distribution of a node given its parents can be quite complex. But you want, in particular, it can't be specified, if you have n parents, you can't specify it with just n numbers. You might need 2 power n numbers. But there can be particular type of distributions, just like noisy R in the previous slide, which can get by with fewer number of numbers. So in particular, you assume, who told you this, but you just go ahead and assume that not only would I consider this to be a Bayes network, but I will consider that this node I, its conditional distribution given its parents is a sigmoid distribution. Sigmoid is actually can be, basically sigmoid becomes a distribution, a probability distribution function. It is a continuous probability distribution function. So, in essence, what I am saying is the probability that Si will be true is essentially 1 over 1 plus e power minus some bias number minus sum of the values of the parents and multiplied by the weights. This is a distribution. To provide this distribution, all I need to give is the weights. Worlds collide now. Suddenly neural networks are the same as Bayes networks are the same as neural networks. Okay? That actually, these are called sigmoid belief networks. What really, at that particular point, if you look at that course, what Hinton was thinking is these sigmoid belief networks, those are the things that will really make neural networks work. While he was giving this course, his students were showing, yeah, none of this is actually needed. Old stuff that was done 10 years back will still work. So now you want to learn about capsule networks? Hinton can be wrong. Hinton thought this was needed, but it wasn't needed. But it's very useful to understand that you can view a neural network as a Bayes network and vice versa. And that in fact, if you do that, you think in terms of parameterized distributions. Okay? Let me take a true-false question, and then we can also that would be your attendance for the first part. That's the only required part. Think about the questions. All you need to say is what your answer is. I'm just trying to kind of be in the mood for combining everything. That question combines logic and probability. And it's a simple enough question. But so think about it yourself. Don't think about it in other ways. I'm going to start answering the question. Please answer true or false. Okay, I'm going to start with this. So here's the way we'll do the rest of the thing. After that, come and take some more raspberry bars, and then we'll do the rest of it. Okay. So if you give your answer, then come down and take more things to eat. I don't want to carry all of the and then the other thing to think about this is to make your Thanksgiving life much better. So the final exam will have 2 parts. One part will be true false questions like this. Okay? And these will have negative marking. And this is important not for the men among you because you have false confidence. It's important for women among you because studies have shown that women tend to do badly when there is negative marking. And it looks like I'm being extremely sexist. But the point is, I do want to make sure that people just don't randomly guess. But I want to tell the women among you that feel more confident. You know, if you think it's a higher chance of your answer being right, do that because in expectation the negative marking won't be held against you. But again, this is the kind of thing. We are slaves to our predilections. But part of education is knowing that and trying to overcome it. Okay? So there will be negative marking for true false questions. That would be the thing where I will make sure that you paid attention all through the semester. And those of you who basically, obviously, the midterm that I gave didn't really require having to listen to my whole semester. There's a lot more that's going on in the class. Okay? So I'm hopefully going to catch some of that in the true false things, and then there would be, and that is more likely than not, this true false thing would be sort of on blackboard and timed exam. But you can do that, okay, still. And then there will be a written part that will essentially be mostly be focused on the things that have happened after the first meeting. Okay, in particular neural networks and logic and Bayes networks. And I realized that we won't have time for logic and Bayes networks to have actual graded homeworks. So what I'll do today is I'll give you some sample problems with solutions. Okay, and it's up to you to try and figure out them now or figure it out after I give you the take home. And if you do that later, don't complain to me that it took too long to do the take home. If you start learning the entire course after you see the exam, it can take an entire semester. Okay, and that's a reasonable thing to be able to understand. Okay, so is this thing done? Are you guys done? 77 answers, 78 answers, one more than I think we have more. Are there any more people here that are doing? Okay, I'm going to start. There are people probably in the cyberspace who are just desperately typing through our files. Okay, so tell me what is the answer here? I don't know what you guys said. I just told it as an attendance. But is this actually supposed to be true or false? How many of you said, so I said, if you know the knowledge-based KB does not entail a fact F, then the probability of F given KB is equal to 0. That's what I said. Okay, how many of you thought that is true? Okay, how many of you thought that is false? How many of you didn't think? Save the thinking for later time. So essentially it's false, right? Because if you don't entail F, doesn't mean you entail not F. This is saying, all they are saying is if you can't entail F, you know the probability of F given KB is not equal to 1. That's all you know. You don't know that it is equal to 0. You will know that it is equal to 0 if in fact KB entails not F. You see what I'm saying? So that's the level of sadism that I have. To try and connect things. Hopefully, I thought about this and I was feeling particularly good. I was going to put on the exam, and because it's Thanksgiving, I decided. So there's this beautiful saying by Johnson, who wrote the first English dictionary, Samuel Johnson, Boston and Johnson, by Johnson. Okay, so he said he gave this thing about writing an essay. After you wrote your essay, go through it carefully, marking all the parts that you thought were exceptionally well put. Remove them, rewrite the essay. So I thought that was an exceptionally well put question, so I gave it away. So hopefully the rest of the exam will be easy. We're going to move on to the second part, which is going to be Bayesian inference. and the inference on these networks. Okay. So, first things first, inference, that is computing the probability in the given a network, computing the probability. By the way, this is actually saying that in the old days, originally, the way Bayesian reasoning started is using the medical expert systems. And one of the medical expert systems is this Pathfinder. And if you read it carefully, they had multiple versions of it. In the beginning versions was just logic. Then they threw in certainty factors. Then they finally threw in Bayes networks. So they lived through all these problems that I was talking about 2 classes back. And they actually found that Bayes network 1 did much better. And they did the Bayes network by assessing the probabilities, by talking to the experts and writing those probabilities down, and then using the probabilities to essentially decide the, whether, a particular given set of symptoms, whether a particular disease is actually there or not. Okay. So in general, given a network configuration, computing the probability that a specific, so in general in Bayes network, what I would give, I'll give the network and I will give some number of evidence variables, and the queries will be what is the probability that some particular fact F is true given some evidence P. That's the usual kind of questions that you ask in Bayes networks. Okay, so in the burglary and earthquake scenario, you might, for example, say, I just saw John calling. What's the probability that earthquake occurred? Okay, and so the evidence doesn't have to be diagnostic or causal. It can be, I can give you causal evidence and ask for diagnostic query and vice versa. So for example, I can say, I know that earthquake occurred. What's the probability that John will call? That would be a causal direction. Or I'll say, I'm just getting a call from John. Should I start worrying whether there was a burglary? That would be a diagnostic thing. I can have inter-causal. So for example, I see that John is calling. I notice on the TV that people are running on the street saying earthquake, earthquake. Okay, what is the probability that Mary will call? You see what I'm saying? Or what's the probability that my alarm is actually working today and it's going off? Why you want to ask that question is it's up to you. But these are the kinds of questions you'll ask normally in a research. Now, given a probability distribution, computing any single probability is the computation. And you shouldn't be surprised that in the worst case, that can be exponential. Why? The simplest way you can see it is logic is a special case of propositional logic is a special case of propositional probabilistic reasoning. Right? Logic basically, you can write everything in logical database as a Bayes network, where the CPTs will only have ones and zeros. We will do that in this last project. It's a special case of Bayes networks. So if you can find some way of doing polynomial time inference on Bayes networks, then you get a Turing award. Right? Because you also showed that logical reasoning is essentially polynomial. But then this poor Steve Cook, who got a Turing award, already said that's not possible. Okay, so that's one way of figuring this out. So in fact, this particular thing shows that a T-SAT problem, a satisfiability problem, which is actually the canonical NP-complete problem, can be reduced to probabilistic reasoning. I'm sorry, vice versa. Yeah, so you can reduce T-SAT to exact inference. Okay, which means if you can solve exact inference in polynomial time, you should be able to solve exact, T-SAT in polynomial time. But we know that T-SAT can't be solved in polynomial time unless P equal to N. That's just some theory saying that you expect things to be bad. Okay, the question of course is, in logic we for example knew that in the worst case, the theorem proving is co-NP complete. The full theorem proving. But there were special cases for which theorem proving was easy. Remember any special cases? That could be true and false, depending on your things I put in. Yes?
Is that like
Mod exponents. could have kept it to yourself. That next one first. Okay, modus ponens, right? And so, if your knowledge base to be able to do just modus ponens and solve everything, your knowledge base should have been in Hahn class form. If your knowledge base was in Hahn class form, then modus ponens would be sound as well as complete. It anyway is sound, but it will also be complete, and then the inference will only be polynomial. So, what would be the equivalent of that for Bayes networks? It turns out that for Bayes networks, in general, the thing to think about is the topology of the network. You talk about singly versus multiply connected networks. A singly connected network is one where between any two variables in the network, if you just ignore the arrow directions, there is exactly one path. Between any two variables, there is exactly one path. At most one path, not exactly. At most one path. If they are disconnected, there is no path at all. If they are connected, there is, and if you ignore the arrow direction, there is one. A multiply connected network has more than one path. This side are singly connected networks. The top one is the favorite chain that people were into last time around, linear chain. This is the reason people like Markov chains. Markov chains are Bayes networks which are singly connected. And they are easy. They are actually polynomial type. And there is another type of network, by the way. There is one more kind of a network which looks like this. And then these are called state nodes. And then at each node there is an observation node. And these can be observed. These are interior nodes. You don't know what they are. What is it called? Hidden Markov model. This is what I told you. Bayes networks are so powerful that everything else becomes just a special case. Neural networks are just a special case of sigmoid belief networks. Right? And Markov chains are the special case of singly connected, fully observable network. Hidden Markov models are the special case corresponding to singly connected but not fully observable. In the sense, during the training, you will never know the state. In the training data, you won't be given the values of the states. You will only be given the values of the observations. So how many of you know Qualcomm? Who started Qualcomm? Viterbi. This is very important because very few professors really make it big in real life. Okay, Viterbi is one of them. Before he started Qualcomm and became a billionaire, what was he doing? He wrote the Viterbi decoding, which was essentially doing fast inference on hidden Markov models. And it turns out to be a special case of Bayes network inference. Okay, and then there is also this issue of learning the parameters of the hidden Markov models. That winds up doing EM, expectation maximization, because it corresponds to the case where some nodes don't have values in the training data. You don't observe them. But the beauty is all of these networks, including our tried and tested Perl network, are singly connected. So in the inference case, there are two parts. The hidden versus non-hidden is only about learning. But if I give you the network with all the CPTs, then in the inference for these networks is exact inference on these networks is polynomial. So this is like the modus Hahn classes for Bayes networks. Multiply connected network, you have seen at least one bad guy. This one you've been seeing all along, right? This is how monsters look. Okay, it has between cloudy and vectors, there are two paths. That's multiply connected network. It turns out, of course, if it's not singly connected, the other case is multiply connected. That's where the worst case actually happens. So doing inference on multiply connected networks in the worst case can be illegal. if you are doing exponential inference on singly connected networks, that's because you probably are also writing exponentially costly sorting algorithms. It will take a bit of space. Okay? There are exact algorithms that actually use the special structure to do polynomial type of derivation. That's why one of the reasons why things that you probably heard of, the versions of Bayes networks you probably heard of, like hidden Markov models and Markov chains, they all are actually singly connected. Okay. Similarly, Prolog that you have heard of in logic is sort of modus ponens. Not surprising. Now, before I go forward, since I know that there is a way of solving, singly connected networks in polynomial time, what if I take this network here and compile this down into this network? Okay, where the problem seems to be the sprinkler and rain. If you can somehow merge them and make a variable called sprinkler rain variable, sprinkler dash rain variable. So sprinkler can be true or false, rain can be true or false. Sprinkler rain will be T, true, 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 false, false, true, false, false, four values. You see what I'm saying? So if I did that, then this network can then be this way. Suddenly I have a singly connected network. Since it's almost towards the end of the class, I just proved P equal to NP. Right? Right? I said, if you see this, that's NP hard, but this is polynomial. What happened? Right? What happened is, complexity is a function of the input size. When you compile this network to this network, you increase the input size exponentially. What was the input that you increased exponentially? The truth table. The truth table here was sprinkler given cloudy in the CPT. The CPT was sprinkler given cloudy, which is of size 2, and rain given cloudy, which is of size 2. But here, essentially, it will be 4 values. It's an exponential blow up. Now, so then it became polynomial in the exponentially blown up input space. It doesn't yet, unfortunately, prove P equal to N. Okay? But it is something people do sometimes. If you have a big network, most of which is singly connected, but there are a couple of variables that are allowing multiple paths. You merge them. You'll get a new network. Now the interesting thing is when I merge them, I can compute the CPT for this just from the numbers here. I don't need to go back to the experts. Do you see what I'm saying? In theory, all I did is essentially sort of like going from first order logic, predicate logic to propositional logic by compilation. And propositional logic becomes much larger database. And you can be probably cheaper in that larger database in terms of the experiment. So keep that in mind. Okay, so as I already mentioned, there are different kinds of inference queries. The most useful queries are of this kind. Give me the distribution of some variable xi given some evidence. But there are also other kinds of queries which can be conjunctive queries. Xi and xj given some evidence. You might want MPE, most probable explanation. Okay, I basically just. So in fact, it turns out most probable explanation is what Viterbi became famous for. Okay? In essence, what he was saying is, in the hidden Markov model, I heard O1, O2, O3, O4. So in fact, as I'm speaking, I'm trying to say certain particular words. In my own mind, I'm saying that correctly. But then I produce sound. So I have accent, and you have bad ears. Okay? So you are getting observations of my phonemes. Now what you want to hear is what did Rao say, but what did Rao want to say. What did Rao want to say are the states that you didn't C. What you heard are the phonemes that I said with my accent, with your values. And then, given all these observations, I want to know what exactly is the sentence that Rao wanted to say. You know, it looks like I could have sworn that this middle word, he seemed to suddenly say cat. He can't possibly be talking about cat in a respectable AI class. But then overall sentence probably still makes sense, you know, and maybe the cat was the wrong one. And that is figuring out the most probable state sequence that Rao was trying to give you based on the observation sequence you got. That is called Viterbi decoding. Okay, in hidden Markov model. And so that is basically the most probable explanation. And there are other kinds of things, but this one actually is quite a useful thing in Markov models. So what I'll do in today's class really is give you the 0th idea for doing inference on Bayes networks. You almost know, below 0th idea you already know, which is take the Bayes network, convert it to a full joint distribution, then you know how to solve it. Okay, I will do it a little better than that, okay, which is, so this is the 0th order. This is basically, you know, we can always compute the joint distribution. Given the joint distribution, we can answer everything. You know this already. Okay, but obviously doing it this way for large networks is extremely wasteful. Okay, so instead, I want to do basically inference by enumeration of only the part of the network that is needed to answer that way. So here's the idea, right? Suppose in this network, I wanted to get the distribution of burglary. Distribution of burglary is burglary true and burglary false. Given some evidence. The evidence is John called and Mary called. You get this? Okay, so I'm in this network with all the CPTs are already there. I didn't show you, but there are CPTs. But I just want to see what's the probability that burglary is true given John called Mary called. What's the probability burglary is false given John called and Mary called. So typically you think of evidence nodes, you know, by just sort of shading them. Those are the evidence nodes. You know their values. And you want the distribution of the rest of the values, nodes. In general, computing this distribution again is called computing the posterior distribution. Okay, so you already have, notice that probability distribution for B was already given in the network. But that's not what I'm asking for. That is prior distribution of burglary. But now that I've given some evidence, your belief in burglary changes. It's no longer the prior distribution. It is the posterior distribution. And then as the evidence keeps accumulating, posterior distribution keeps changing. Is the probabilistic logic monotonic? No, because posterior distribution keeps changing. As the evidence changes, so will my belief. So this is how actually this became a useful thing for us. Okay, continuing back. So this one, P, B given J and M, I can write this. You know, anytime I write capital letters, that is essentially think of it as the distribution. That means you can have that variable will take all its values, equal to true, equal to false. J means J is true, M means M is true, and not J means J is not true. Okay, so I can write this. You know, I can always write P A given B C as P A B C by P B C, right? That's all I did here. Except I just allowed this to be B. So in fact, this is two equations, it's a set of equations. One for B equal to true and one for B equal to false. Yes?
B is a random variable?
No, B is this burglary variable. They're all random variables. They're all Boolean random variables. And these random variables values I observe, J and M. Now notice that to figure out the distribution of posterior distribution of B given J and M, I need to essentially go through the joint distribution, honestly. But my hope is I won't look at the entire joint distribution, only look at the piece of it that really matters to me. So that's what I'm doing here. So I come up to here, this part, people understand this, right? Now I will do this. Well, I don't really need to compute PJM because I'm actually computing the distribution. So I can think of 1 over PJM to be alpha. Remember, I spent a humongous amount of time last class saying, if only you don't need to have to compute evidence. It is just assumed that you understand this. In every Bayes network inference algorithm, they just throw in an normalization constant. And they assume that you know that you can eliminate that normalization constant. Because in the end, you will get probabilities like 9 and 7. With the expectation that the real probabilities are 9 by 9 plus 7 and 7 by 9 plus 7. Get this, right? So, this part you are. Now I need to just write probability of B being true, J true and true, probability of B being false, J true and true. That's what I need to write. Unfortunately, it can't be read from the network here. So now, basically what this is it's missing some of the variables in the network that are not being named here. Because burglary is there, John is there, Mary is there, but so are alarm and earthquake. So what I really need to do is to say that this really is the marginalized version of the joint distribution. Anything that's not appearing in a conjunctive probability, it's been marginalized out. It was integrated out. So essentially what I'm saying is the PJM is really nothing but PEAJM, where E and A are marginalized out. That means they took both true and false values and you added up those numbers. People get this? Right? Okay? Now this is stuff that you know and love. This is a joint distribution entry. Every joint distribution entry is nothing but a multiplication of the numbers from this network. So I will continue and say this is nothing but PB and PE and PA given BE, PJ given A, PM given B. I'm just using the network configuration. I can just stop this. This is like fine, but I can also realize that there is a summation going on over E and summation going on over A. You can pull the summations inside and see which parts actually, depend on E and which parts actually depend on A. So when I pull the summation inside, so the A part is only here, so I pull the summation up to here. The A summation up to here. And the E summation just stays here because E part is here. So actually, if you just understood up to this point, you already know which joint distribution entry numbers you have to add up to get the value that you want. This one is saying you don't need to even compute those joint distribution numbers which requires multiplications multiple times. You can actually compute them more efficiently. And in fact, if you look at this,